The phase diagram for water is represented in the PT coordinates to the right. Identify the regions labeled A, B, and D in this order. Now let's see the diagram. A is the solid phase, B the liquid phase, and D the gaseous phase. So obviously in that order A, B, and D we should have solid, liquid, and gas. So that should give us B. What is the distinguishing property at point J? So let's look at point J. You see, point J is the point where the solid, liquid, and gaseous phases are coexisting. So that should be C. The liquid and vapor and solid phases are coexisting. Now question 3 says point C is referred to as, now you see that's point C. This is the point where we can't distinguish between the liquid and gaseous phase, so that is known as the critical point. Obviously B should be the right answer. 4. The saturation vapor pressure is the pressure at which the liquid and vapor phases are in equilibrium. So that's kind of obvious. Saturated water occupies a volume of 1.2 meters cubed. Heat is added until it is completely vaporized. If the pressure is held constant at 600 kilopascals and the specific volume of saturated water Vf is 0.0011 meters cubed per kilogram, what is the mass of saturated water in kilograms? So obviously the answer should be 1091 kilograms. But I think you want to know how this answer is gotten. First of all, those are the givens. Now let's look at some basic formulas. The specific volume is given by the volume divided by the mass, but this is the case of saturated water. So if we make mass the subject, we're going to have the mass of saturated water, that's mf, to be equal to capital VF on small vf. So we know capital VF is 1.2 meters cubed and small vf is 0.0011 meters cubed per kilogram. So when we have that substituted, this is what we have here. We can even look at the units. So meter cube, we take care of meter cube, so we just left kilograms. Now that gives us mf equals to 1090.909091 kilograms. So I think you should verify that answer with your calculator. So when we round up to the nearest unit, we're going to have mf equals to 1091 kilograms. Question 6. Calculate the final volume in meters cubed, given that the specific volume of saturated water vapor Vg is 0.3157 meters cubed per kilogram. So obviously the answer there is D, that's 344.4 meters cubed. So let's find out how to get that answer. Water completely vaporizes, which means that mg equals to mf. So here there must be conservation of mass, because that's all the mass of water that was there before must be equal to the mass of water after, that's in the vaporized form. So that's why we have mg equals to mf. Now we start with the specific volume of the saturated water vapor. So we have Vg equals to capital Vg on mg, where capital Vg is the volume of the saturated water vapor and mg is the mass of the saturated water vapor. Now if we make capital Vg the subject, we're just going to have specific volume of saturated water vapor times mass of saturated water vapor to be equals to capital Vg. Now we know that mg equals to mf, so we're going to have that substituted over there, so that we have Vg equals to mf times small vg. Now we recall that the mass of saturated water was calculated in the previous question to be 1091 kilograms, and the specific volume of saturated water vapor Vg has been given to be 0.3157 meters cubed per kilogram. So when we do this evaluation, we should have Vg approximately equal to 344.4 meters. Energy is added to a piston cylinder arrangement, and the piston is withdrawn in such a way that the quantity PV remains constant. The initial pressure and volume are 200 kilopascals and 2 meters cubed respectively. If the final pressure is 1000 kilopascals, calculate the work done by the gas on the piston in kilojoules. So the answer there is B, 277 kilojoules. Let's see. First of all, it's told in the equation that PV remains constant, so PV is equal to constant. We can call that equation 1. Since initial conditions have been given, we can write the first equation. Thus, we have been given the initial pressure and the initial volume, so we can conveniently write P initial, that's Pi, times V initial, Vi, to be equal to constant. Call that equation 2. Now, the work done by the cylinder is given by, you can recall from first principle that the work is given by the integral from V initial to V final of P dV, called that equation 3. Now, if we substitute 1 in 3, that's if we make P the subject here, we're going to have constant on V. So we have that substituted in 3, and that's what we have here. Now, we'll take out the constant out of the integral, and that gives us W equals to constant times the integral from Vi to Vf of 1 on V dV. So when we do that integration, we're going to have W equals to constant into ln natural logarithm of V with the limit Vi Vf. So we'll call it equation 4. Now when we substitute 2 in 4, because we know that the constant is Pi times Vi, so we have that substituted there, and we'll take care of the limits. That's we expand what we have in brackets there. We're going to have this, so we have W equals to Pi Vi ln Vf on Vi. That's the natural logarithm of Vf on Vi. So that's when you expand these brackets. So we'll call that equation 5. Since Vf is not given, we use the ideal gas equation PV equals to nRT to change to pressure. So you can actually see in the equation the final pressure was given, but we don't have the final volume, so it would be preferable to work in pressure. So we're going to make use of the ideal gas equation. So we make V the subject there, and that gives us nRT divided by P. Now we know that we are dealing with an isothermal process because PV remains constant, so it is an isothermal process. Now we just have the initial volume to be given by nRT divided by Pi. N is the number of moles of gas in the cylinder, and we have Vf equals to nRT divided by Pf. So you can actually see that T is the same for the two states. Now we're going to have this substituted in equation 5. So 6 in 5 will imply that W is equals to Pi Vi times the natural log of nRT on P final divided by nRT on P initial. So we've had Vf and Vi substituted by the expressions here. That's Vi and Vf, which are the expressions we have just had. Now that implies that W is equals to Pi Vi times the natural log of Pi on Pf. So when you try to simplify these brackets, you see nRT cancels out to nRT, and when you adjust, you have 1 on Pf divided by 1 on Pi, which becomes Pi divided by Pf. So at this point, we just do our numerical analysis. Thus, we know that Pi is given in the equation as 200 kilopascals. Vi, the initial volume, is given by 2 meters cubed. Pf equals to 100 kilopascals. So when we have that substituted in the last equation we have there for the work, we're going to have W equals to 200 kilopascals times 2 meters cubed times the natural log of 200 kilopascals divided by 100 kilopascals. So here the kilopascals cancels out the kilopascal down here, and here we have kilopascals times meters cubed. So that's what gives us a kilojoules, and we are not obliged to do any conversions to the SI unit. So we're just going to have W equals to 277.2588722 kilojoules after simplifying that expression there on the right hand. So when we round up to the nearest unit, we're going to have W equals to 277 kilojoules, which is just what we have there as B. It's the option of our answer. A piston moves upward a distance of 5 centimeters while 200 joules of heat is added. Calculate the work done in joules to raise the weight and compress the spring. So there the answer is 250 joules. So that should be the work done to compress the spring. Now this is our diagram. Let's try to analyze what we have in the diagram. We have a piston of mass 60 kilograms. We have a spring attached to the piston with spring constant K equals to 50 kilonewtons per meters. We have water vapor in the cylinder. We have heat added cure, and the diameter of the cylinder given as 20 centimeters. Now let's try to examine the piston. So that's the piston there. in the piston we have water vapor, so in the cylinder we have water vapor. So the water vapor exerts a pressure Pg on the cylinder, and we know that pressure is given by force times area. So the force exerted by the water vapor on that cylinder is given by the pressure exerted by the water vapor times the area of the piston, which is also the area, the cross-sectional area of the cylinder. That's why we just have PGA for the force exerted by the water vapor. Now, acting downwards is a spring force, because we know that the piston is attached to a spring. So when the spring is compressed, it exerts a downward force, F spring, on the piston. So that's what we have there. In addition, we have the weight of the spring acting, of the piston acting downward. So that's mpg. Here mp is the mass of the piston and g is the acceleration due to gravity. Also, we have to note that the cylinder is exposed to atmospheric pressure, so we must have atmospheric pressure acting on the piston, and that exerts a force at P atmosphere times A, because it's acting on the area of that piston. So these are all the forces acting on the piston. Now let's choose our x direction to be vertical and the y direction horizontal. Equating forces in the x direction, that's we try to resolve the forces in the x direction and form an equation. We're going to have PGA equals to P atmosphere times A plus F spring plus MPG. So downward forces must be equals to upward forces if for the piston to be in equilibrium. So that's what we have here. You can see the only upward force is PGA, and the downward forces are P atmosphere A, F spring, MPG. So that's what we have there. Now let's make PG the subject, and that gives us PG equals to P atmosphere times A plus F spring plus MPG on A. Work done by the gas is given by W equals to the integral from VI to VF of PG dV. So from first principle we know work is equals to the integral of P dV, but in this case our P is the pressure of that water vapor, which is in the gaseous state, and the change in volume from VI to VF. Now we have to substitute PG, which was just obtained from our first considerations, in the expression for the work, and that gives us what we have right here. Now we only have to do a little bit of substitutions. So we can see that dV is given by A dx, because the cross-sectional area is constant, so only variations in the x direction can be observed. So obviously if the piston has to displace in the x direction, because we have chosen our x direction to be vertical, if the piston displaces itself in the x direction, then we're going to have an elementary distance dx, and if you multiply this elementary distance with the cross-sectional area, we're going to have the elementary volume. F spring is equals to kx. We know that the spring force is a linear function with k constant of the spring. Now when we have this substituted in the work above, we have W equals to integral from xi to xf, so it's no longer vi to vf because the variable now is x. So we have to have x, the initial x position, to the final x position of P atmosphere A plus kx. Now F spring has been substituted by kx plus mpg divided by A times A dx, where we have dv substituted with A dx. Now you can obviously see that A cancels out with this A, and that will result to W equals to the integral from xi to xf of P atmosphere A plus kx plus mpg dx. Now we just simply do our integration of each of the terms, and when you do that, the first term there we have P atmosphere Ax, because this is a constant, so you just have x there from xi to xf as our limit. The second term kx, when integrated, we have half kx squared, we have from xi to xf, and the last term mpg, when integrated, we have mpgx from xi to xf. After substituting the limits, this is what we have. so we'll just have our limit substituted. That's the expression we have. Now let's record that E is equal to pi d squared on 4, because we have been given the diameter of the cylinder, and that area there is the cross-sectional area of that cylinder, which is also the area of the piston, and that's pi d squared on 4. Now when we have that substituted in E, we have this expression. So what has changed is E. We now have pi d squared on 4 substituted for E there. At this level, we just need to recall our parameters to substitute. P atmosphere is equal to 1 times 10 to the 5 Pascal. D, the diameter of the cylinder, is 20 centimeters, which is 0.2 meters. Now, we have been told in the equation that the piston moves a distance of 5 centimeters upwards. That's it raises. So we can take our initial x position to be 0 and the final x position to be 5 centimeters away from 0, so that we just have a change from 0 to 5 centimeters as 5. So converting this to meters, we have 0.05 meters. K, the spring constant, is 50 kilonewtons per meter, which is equal to 50 times 10 to the 3 newtons per meter. The mass of the piston, MP, is 60 kilograms, and the acceleration due to gravity is 9.81 meters per second square. So we're going to have all these parameters substituted in the expression for the work, and that's what we have right here. So each of the known values has been substituted. So when you do this simplification, you're going to have W equals to 251.051667 joules. So when we round up, you can have this to be W equals to 250 joules, because it's quite close. So obviously the answer was to be 251, but with the options given, the nearest answer should be 250. First law of thermodynamics: calculate the change in internal energy of the vapor if the spring is originally unstretched. So the answer there is minus 50 joules. According to the first law of thermodynamics, delta U is equal to Q minus W. So we know delta U is a change in internal energy, Q is a heat, and W is the work done by the system or on the system. Now we have been given Q in the equation to be 200 joules, but it is positive because this heat is put into the system, and we have calculated the work to be plus 250 joules because the system does work on the surrounding. Now when we have that substituted in the equation, therefore the change in internal energy, we're going to have delta U to be equal to plus 200 minus plus 250, and when we do the simplification, we're going to have delta U equals to minus 50 joules. The air in the cylinder of an air compressor is compressed from 100 kilopascals to 10 megapascals. Estimate the final temperature if the air is initially at 100 degrees Celsius. The ratio of specific heat, K, equals to 1.4. So the answer there is C, 1390 Kelvin. Let's recall that PV raised to the K is equal to constant. So that implies that PI VI raised to the K is equal to PF VF raised to the K. So the I there is for the initial conditions and F is for final state. Assuming the air in the cylinder behaves as an ideal gas, we have PV equals to nRT. So here that implies that V equals to nRT raised on P. That's equation 2. So at this point we are trying to introduce the temperature, but we are eliminating the volume because we don't have information about the volume. So we'll try to eliminate that because we have information about pressure and temperature. Now when equation 2 is substituted in 1, taking into consideration the states initial and final, we're going to have Pi times nRTI on Pi raised to the K to be equal to Pf times nRTF on Pf raised to the K. So when we simplify that, we're going to have Pi into Ti on Pi raised to the K to be equal to Pf into Tf on Pf raised to the K. So you can clearly see that nR cancels out with nR because it's common and they have the same powers. Now at this point, we're going to have on the left hand side Pi raised to the 1 minus K, and on the right hand side Pf raised to the 1 minus K. Then for the temperatures, they are both raised to the power k. Now you can clearly see that in the brackets we have Ti on Pi raised to the k, which is the same on both sides. When you take out Pi, it becomes Pi on Pi raised to the k, and by the laws of indices, when you're dividing quantities of this with the same basis, you simply subtract the indices, so we just have 1 minus k, and that's what we have there. Now at this point, we'll just make Tf to the power k the subject. So when we divide both sides by Pf raised to the 1 minus k, this is what we have. Now you can see that Pi and Pf have the same indices, that's 1 minus k. So we can rewrite that as Pi on Pf raised to the 1 minus k, so because the indices were the same, times Ti to the k to be equal to Tf raised to the k. Now when we raise both sides to the 1 over k, it gives us Tf to be equal to Pi on Pf raised to the 1 minus k on k times Ti. So at this point, we simply find the parameters which we need to substitute. So we have the final pressure given as 10 megapascals, which is 10 times 10 to the 6 pascal. We have the initial pressure 100 kilopascal, which is 100 times 10 to the 3 pascal. We have the initial temperature, which is 100 degrees Celsius equals to 373 Kelvin. So to change to Kelvin, we simply add 273 to the temperature in degrees Celsius. Then we have been given K to be 1.4. So we're going to have that substituted in the expression for Tf, and that's that. And from here, we use our calculators to evaluate and see what answer we obtain. So after evaluation, we are supposed to have Tf to be equal to 1390.392458 Kelvin. But if we round up to the nearest unit, we're going to have Tf equals to 1390 Kelvin, which is exactly what we just have there as C. Consider a frictionless piston cylinder assembly containing 500 grams of monoatomic helium gas with a molar mass m equals to 4 grams per mole. In the initial state 1, the volume occupied by the gas is V1 equals to 100 liters, and the corresponding temperature T1 is equals to 600 Kelvin. Assuming helium behaves as an ideal gas and that the internal energy of an ideal monoatomic gas at a temperature T is given by U equals to 3/2 nRT, where N is the number of moles and R equals to 8.31 joules per mole per Kelvin is a universal gas constant. So this is the piston cylinder assembly, and that's the helium gas right in there. Calculate the specific heat of helium gas at constant volume CV of helium gas in kilojoules per Kelvin per kilogram. So right there, the answer should be 3.12 kilojoules per Kelvin per kilogram. Let us find out how to get that answer. Now let's recall that from the first law of thermodynamics, du is equals to Q minus W. At constant volume, du is just equals to Q. So that permits us to write du equals to Cv dt. Now Cv, when made the subject, is equals to du on dt, but the specific internal energy is given by the internal energy divided by the mass. So we're going to have that substitute there for u, small u, and that gives us Cv equals to du on m dt to be equals to 1 on m, when we factor out 1 on m, du dt. Now we have been given u in the question as 3/2 nRT, so we have that substituted there, and from there we can differentiate. So we have Cv equals to 1 on m d 3/2 nRT dt. So when we differentiate this term with respect to t, we're just simply going to have 3/2 nR. So we can also remember that n, which is the number of moles, is equals to small m on capital M, where m here is the mass of that gas and capital M the molar mass. So when we do that substitution for n there, we have Cv equals to 1 on m into 3/2 small m on capital M, as the substitution for n, times R. So you can clearly see that m here cancels with small m there, and we're left with Cv equals to 3R divided by 2 times capital M. Now let's just see what values we need to substitute. the universal gas constant R is equals to 8.31 joules per mole per Kelvin, which is the same as 8.31 kilojoules per kilomole per Kelvin. So you can actually see that nothing changes here because the kilos can still take care of themselves. Now the mass, the molar mass is 4 grams per mole, which is still the same as 4 kilograms per kilomole. So I'm going to have this term substituted there, and the reason for all this adjustment is because we want the final unit to be kilojoules per Kelvin per kilogram. Now when we substitute there for CV, we're going to just have 3 into this is the universal gas constant, which is that we have just had, time divided by 2 into the molar, which is what we have modified. So we can see that kilomoles per kilomole here and per kilomoles here cancel out, so we'll just be left with kilojoules per Kelvin. Then when the kilogram goes up to the numerator, it becomes per kilogram. So using your calculators, you should have an answer very close to 3.12 kilojoules per kilogram per Kelvin. So that's the constant volume specific heat. By moving the piston, the gas undergoes a reversible isothermal expansion to a state 2, where the volume V2 equals to 250 liters. Calculate the pressure P2 of the gas in state 2 in Pascal. So there the answer should be 2.49 times 10 to the 6 Pascal. Now let's see. Process 1-2, which takes us to state 2, is an isothermal expansion. So P1 V1 must be equal to P2 V2. Has been set in the equation isothermal expansion. So that's why we can use the relationship P1 V1 equals to P2 V2. Now when we make P2 the subject, because that's what we are interested in, we're going to have P1 V1 on V2, which we're going to call equation 1. Then now we have a little problem. We have V1, that's the volume at state 1. We have V2, the volume at state 2, but we don't have P1, the pressure at state 1. So we're going to look for an expression to substitute for P1. Helium behaves as an ideal gas, so we have P1 equals to nRT1 on V1. That's from the ideal gas equation. And we can remember that N here is the number of moles, and when changed by the ratio M on capital M, we just simply have now mRT1 on capital M V1 for P1, which we call equation 2. So substituting 2 in 1, we're going to have P2 to be equal to, this is the expression we've had for P1 times V1 on V2. So you can clearly see here that V1 cancels out with V1 there. So that just simply results to mRT1 divided by capital M V2. So at this point, we need to just get the numerical values of mRT1, capital M, and V2. So in the equation, we're given M, the mass of the helium gas, to be 500 grams, the molar mass to be 4 grams per mole, the universal gas constant R to be 8.31 joules per mole per Kelvin, the initial temperature, that's the temperature at state 1, that's T1, to be equal to 600 Kelvin. Then the final volume, that's V2, the volume at state 2, is given as 250 liters, and to convert to meters cube, we divide by 1000, which gives us 0.250 meters cube. So we're just going to have this substituted in P2, and that's just what we have there. Now we can study the units and see if it results to Pascal. Now here, grams cancels out with gram, per mole cancels out with per mole, Kelvin cancels out with Kelvin, so we're going to be left with joule on meter cube, and this joule on meter cube is what results to the Pascal. So dimensionally, okay. So when that is done, this evaluation on the right hand side, we're going to have 2,493,000 pascals, and when written in standard form, we have P2 equals to 2.49 times 10 to the 6 Pascal. So that's just A, which is what we have. Calculate the work 1-2 done in the course of the isothermal process in kilojoules. So here the answer must be 571 kilojoules. Let's see. The process 1-2 to state 2 is an isothermal expansion. We have already seen that. So we can now write PV equals to constant. So for an isothermal expansion, PV is a constant. Now that permits us to write P2V2 equals to constant. And the reason why I'm using 2 is because we have the pressure at state 2 and the volume at state 2. So we will just use this as our constant. Now the work done in the course of the process is given by W12, which is equals to the integral from V1 to V2 of P dV. We call that equation 3. So when we make P, the subject in equation 1, we're going to have constant on V, and when we have that substituted in equation 3, you're going to have W12 to be equal to integral from V1 to V2 of the constant divided by V dV. Now, when we take out the constant, we are going to have W12 equals to constant times the integral from V1 to V2 of 1 on V dV. So integrating what we have there, we're just going to have constant times the natural log of V from V1 to V2, which is equation 4. Now, when we have equation 2 substitute in 4, that's our constant there, we're going to have W12 equals to P2V2 for the constant. And now when we take care of this limit, that's the natural log of V from V1 to V2, that's when we have that substituted, we should have the natural log of V2 on V1. So we can always remember from our laws of logarithm, first of all, when you have the limit substituted, we should have ln V2 minus ln V1. And from our laws of logarithm, when you're subtracting, you just simply have natural log of V2 on V1, which is right there what we have. So we call this equation 5. Now at this point, we know P2, V2, V2 and V1 here, so we simply find their numerical values. Now P2 is 2.49 times 10 to the 6 Pascal, which is what we had calculated in the previous question. V2 equals to 250 liters, which was given in the previous question, and that is equal to 0.250 meters cubed when you divide by 1000. When we do that for V1, we'll see that 100 liters is equal to 0.100 meters cubed. So I'm going to have these parameters substituted in equation 5 to get the work done in the process 1, 2. Now when we substitute, we're going to have W12 equals to 2.49 times 10 to the 6 Pascal times 0.250 meters cubed times the natural log of 0.250 meters cubed on 0.100 meters cubed. So obviously meters cubed cancels out meters cubed there. Yeah, we have Pascal times meters cubed, which gives us the joule. So first of all, our answer comes out in joules. So we're going to have 571,076.1986 joules. So converting that to kilojoules, we're going to have 571.0761986 kilojoules. And when we round up to the nearest unit, we just have W12 to be equal to 571 kilojoules, which is C, the answer we have. If we envisage a new process where the gas undergoes an adiabatic expansion between 1 and an intermediate state 3, where V3 equals to V2, followed by heating at constant volume between state 3 and the final state 2 previously defined, determine the temperature T3 of the intermediate state in Kelvin. So obviously the answer there should be 326 Kelvin, but you might want to know why that should be the answer. Now on our PV coordinates, we have the first process that was mentioned in the equation from state 1 to state 2, which was given to be an isothermal process. Now let's see, at state 1 we have V1 and at state 2 we have the volume there as V2. Let's try to envisage a new process. Now from state 1 to 3 is an adiabatic expansion, so you can actually see that during an adiabatic expansion the volume increases, and in the course of volume increasing, pressure has to drop. So that's why you see step point 3 is kind of below 2 and it's below the first curve there. Now the next process is given to be heating at constant volume. So you can see that we're told that heating at constant volume between state 3 and state 2. So you see, when you're at constant volume and you heat, the gas molecules try to expand and a pressure increases. So that's why you have point 3, state 3 below state 2 to indicate that when heating is done at state 3, there's going to be pressure increase, and that results and that goes to state 2. So that's the process. That's the diagram of all the processes mentioned. Now process 1-3 is an adiabatic process, so that means that we can write P1 V1 raised to the gamma to be equal to P3 V3 raised to the gamma, which we call equation 1. So that's from our previous knowledge. Assuming the air in the cylinder behaves as an ideal gas, we have PV equals to nRT if and only if P equals to nRT on V. That should be equation 2. 2 in 1 implies that nRT1 on V1 times V1 raised to the gamma is equal to nRT3 on V3 times V3 raised to the gamma. So actually we're trying to eliminate the pressures because we don't have much information about pressure in this kind of the processes. So that's why we are trying to eliminate the pressures. So I've simply used the ideal gas equation and taken into consideration the states. So that's why we have nRT1 on V1 and we have here nRT3 on V3. So at this point we can only do simplifications. Firstly, you can see that n arrow cancels out with n arrow. Here the bases are the same, so you just simply add up the indices. Now you have T1 on V1 times V1 raised to the gamma to be equal to T3 on V3 times V3 raised to the power gamma, and this results to T1 times V1 raised to the gamma minus 1, because you have V1 to the gamma divided by V1 to the 1. That's why you have gamma minus 1, and that is the same for the V3 on the right hand side. Now our point of interest is T3. We are trying to look for T3, so we'll make T3 the subject by dividing both sides by V3 raised to the gamma minus 1, which results to this. So here we have V1 on V3 all raised to the gamma minus 1 because the indices are the same. So when you divide both sides, since the indices are the same, you can then raise all the ratio to one index. So that's gamma minus 1. Now we look for gamma. So in the equation we have T1, T2, V1, V3 and T3, because we have been told that V3 is V2. That's it, V3 equals to V2. So obviously since we had V2, we can have that substitute for V3. We have calculated, we had T1 given the equation at 600 Kelvin, and now we have to look for T3, but we don't know what gamma is. So that's our point of interest now. We can remember that for the molar specific heat, Cp, because Cp bar is equal to Cv bar plus R, where Cp bar and Cv bar are the molar specific heat capacities at constant pressure and constant volume respectively. And we know that Cp bar is equal to gamma Cv bar, because when you take Cp bar on Cv bar, it gives you gamma. So it simply makes Cp bar the subject, which we are going to have substituted in this expression, because we don't have Cp bar, we have just Cv that we had calculated previously. Now when we have that substituted, we are going to have gamma Cv bar equals to Cv bar plus R. When gamma is made the subject by dividing both sides by Cv bar, we're going to have gamma equals to Cv bar plus R on Cv bar. So when we expand the fractions, as we try to separate each of the fractions, you have Cv bar on Cv bar, which gives you 1 plus R on Cv bar. So this is the expression. From what we have done previously, we had the specific heat capacity small v, small cv to be equal to 3.12 kilojoules per kilogram per Kelvin, and we have R equals to 8.31 joules per mole per Kelvin, which we can write as 8.3 kilojoules per kilomole per Kelvin. Now Cv bar is equals to the molar mass times the specific heat capacity at constant volume. So you can clearly see that when we do this multiplication, we're going to have 4 kilograms per kilomole. So we had earlier seen that we could write the molar mass as 4 kilograms per kilomole times the specific heat we had calculated in the first question of this section as 3.12 kilojoules per kilogram per Kelvin, which will now give us 12.48 kilojoules per kilomole per Kelvin. So you can actually see that the units are the same as that for R. So you can see that that's the molar specific heat at constant volume, because it's here per mole, so it's per kilomole. That's why it's the molar specific heat at constant volume. So when we substitute in the formula we are just obtained for gamma, we are just going to have 1 plus, that's 8.3 kilojoules per kilomole per Kelvin divided by 12.48 kilojoules per kilomole per Kelvin. So you can actually see that the units cancel and this quantity becomes dimensionless. So when you do that simplification, you should have gamma equals to 1.6658653885. Now we recall that we had T3 equals to T1 times V1 on V3 raised to the gamma minus 1. So we can only just extract the parameters we have to substitute in that equation. So T1 was 600 Kelvin, which was mentioned in the equation. V1 equals to 100 liters, which is equals to 0.100 meters cube when you divide by 1000, and V3 is given as V2. So we're told V3 equals to V2, which is equals to 250 liters, and when you divide by 1000 you have 0.250 meters cube. Now we just need to substitute all of this into the equation for T3, and that gives us T3 equals to 600 Kelvin, that's for the temperature T1, times 0.10 meters cube on 0.250 meters cube. So we'll substitute for V1 and V3, and then we'll recall what we have just had for gamma, which is 1.6658653885 minus 1. So when you do that simplification, you should have T3 equals to 325.9693552 Kelvin. So when you round up to the nearest unit, you should have T3 equals to 326 Kelvin, which is the answer we had just seen. Now we are told here to calculate the work 1, 2, 3 done in the successive processes 1, 3, 2 in kilojoules. So there the answer should be 427. I think we should analyze that from the diagram. Process 1, 3 is an adiabatic process, hence we have PV raised to the gamma to be equal to constant if and only if P is equal to constant divided by V raised to the gamma. We call that equation 1. So this is what we know about adiabatic processes, and when you just make P the subject, you result to this. So that's equation 1. So W13 will then be given by the integral from V1 to V3 of P dV, which is equation 2. So when we have equation 1 substitute in 2 so that we can eliminate the pressure, we have W13 equals to, so we can just substitute for P actually. So we have V1 V3 constant, integral from V1 to V3 of a constant on V raised to the gamma dV. Now when we integrate this term, this equation, this expression here, we're going to have constant divided by 1 minus gamma into V raised to the 1 minus gamma from V1 to V3. So we substitute our limits and we have this equals to constant on 1 minus gamma into V3 raised to the 1 minus gamma minus V1 raised to the 1 minus gamma. So we now know that P1 V1 raised to the gamma is equals to constant, because we have the conditions. We know that if PV to the gamma is a constant, then obviously P1 V1 raised to the gamma must also be a constant. And now we can also remember that we did not have information about the initial pressure, that's the pressure at state 1. So we'll just substitute this pressure at state 1 with this expression which we had earlier seen in the previous exercises, so that we just have P1 equals to nRT1 on V1, and we'll have this substituted in this expression. Our constant becomes nRT1 V1 raised to the gamma minus 1. So obviously when you substitute this here, we have V1 at the denominator and V1 to the gamma at the numerator. So that's why you have V1 raised to the gamma minus 1, because it's a division. Now we have this constant substituted in the work done from 1 to 3, so that we have W13 equals to nRT1 times V1 raised to the gamma minus 1 on 1 minus gamma into V3 raised to the 1 minus gamma minus V1 raised to the 1 minus gamma. So I'll just simply substitute for the constant. Now we can also remember that n, the number of moles, is small m on capital M. So that when that is substituted, we have this expression here. So this is W13. So that gives us m equals to 500 grams, capital M 4 grams per mole, R equals to 8.31 joules per mole per Kelvin, T1 equals to 600 Kelvin, V1 equals to 100 liters, which is equals to 0.100 meters cube, V3 is equals to V2 equals to 250 liters, which is equals to 0.250 meters cube, and gamma equals to 1.665865385. So that gives us the work done from 1 to 3 to be equals to this when you substitute all these parameters which we have extracted. So when you do that simplification, you should have W13 to be equals to 427,487.8058 joules. So taking that to kilojoules and rounding up to the nearest unit, you should have W13 to be equals to 427 kilojoules. So the work done from process 1 to 3 to 2 is equals to 427 kilojoules. So here you can see that we haven't mentioned anything about the work done from 3 to 2, but from the diagram it should clearly be seen that process 3-2 is a constant volume process, so the work done there is 0, and that's why it was needless for us to calculate the work done from process 3 to 2. So it just simply boiled down to the work done from process 1 to 3. So that's why we just focused on process 1-3 and finally concluded with this work done for the gas in living process stage 1 to 3 and to 2. What is the change in entropy delta S of the gas between state 1 and 3 in joules per Kelvin in the course of the process 132? Now let's recall that T ds equals to du plus P dV, where S here is the entropy, U the internal energy, and V the volume, P is the pressure. Now we can also write this as T ds to be equal to M du. So where now we have the specific internal energy, so that we can now multiply that by mass to give du plus P dV. Now if we divide all through by T, that gives us ds equals to M du on T plus P on T dV. So we can recall that du equals to CV dt, where CV here is a specific heat capacity at constant volume, and P on T equals to nR on V. This is from the ideal gas equation. So when we have that substituted there for ds, we're going to have ds equals to mCV dt on T. You can see that du has been substituted by CV dt plus nR on V dV. So we just simply integrate both sides. So we're integrating the left hand side from S1 to S3 ds because it's from state 1 to state 2, and we're integrating the first term here from T1 to T3, as we're integrating mCV dt dt on T plus the integral of nR dV on V from V1 to V3. So when each of the integrals is done and the limits substituted, we're going to have S3 minus S1 equals to mCV ln T3 on T1 plus nR ln V3 on V1. So ln there is a natural logarithm. Now at this point, we'll now substitute for the number of moles. We can remember that number of moles given by small m on capital M. So with that, we can just simply extract the parameters from all the information given to us in the equation to substitute there and get delta S, which is simply delta S with S3 minus S1. So that's what we have to get. Now let's examine the givens. We're given this mass of the gas to be 500 grams. We have calculated the specific volume at specific heat capacity at constant volume to be 3.12 kilojoules per kilogram per Kelvin, which we can write as 3.12 joules per gram per Kelvin, because you see the kilos take care of themselves. Then we had calculated the temperature at state 3 to be 326 Kelvin. We are given the temperature at state 1 to be 600 Kelvin, the molar mass 4 grams per mole, the universal gas constant 8.31 joule per mole per Kelvin, the volume at state 3 250 liters, which is actually the volume at state 2 also, and the volume at state 1 100 liters. So we're just going to have that substituted in the equation there for delta S. So this is what we have. Now when we try to evaluate each of the terms separately, that's we evaluate 500 grams times 3.12 times the natural log of 326 on 600 first, we have minus 952. Then when we evaluate this term here, we're going to have 952 joules. So that gives us delta S to be equals to 0 joules. So this actually tells us that the change in entropy between state 1 and 3 is 0 joules. N moles of an ideal gas evolve from an initial state Pi, Vi, Ti to a final state Pf, Vf, Tf. Let gamma equals Cp on Cv be the ratio of specific heat at constant pressure and volume respectively. Express the change delta U in internal energy. So there the internal energy must be D, which is Pf Vf minus Pi Vi on gamma minus 1. Let's find out. Recall the first law of thermodynamics. So from our first law of thermodynamics, delta U equals Q minus W. Now this question is based on the set of questions we have just answered about the helium gas. So we're told in that question, that in the narration, that it's an adiabatic process, so there's no heat change between the system and the surrounding, so Q is actually 0, and we are left with delta U equals to minus W. Now recall that the work is equals to integral from V initial to V final of P dV, and for this case it's adiabatic, so we have P V raised to the gamma to be equals to constant. if and only if P equals to constant divided by V raised to the gamma. Now when we have this value of P substituted in the expression for the work, we have W equals to V integral from Vi to Vf of constant divided by V raised to the gamma dV. Now when we do this integration, we result to this. Now at this point we substitute the limits, so we have W equals to constant on 1 minus gamma into Vf raised to the 1 minus gamma minus Vi raised to the 1 minus gamma. Now we'll expand the brackets, so we'll expand, we'll multiply all through by, we'll distribute this constant over the minus sign there, and we have W equals to 1 divided by 1 minus gamma into constant times Vf raised to the 1 minus gamma minus constant times Vi raised to the 1 minus gamma. Now let's try to find that constant. We are told in it that PV raised to the gamma is a constant, so that means that P initial V initial raised to the gamma must be equal to P final V final raised to the gamma, which must also be equal to that constant. So when we have this constant substituted over here in the expression for the work, making sure that we substitute the constant that has F where we have F, and the constant that has for the initial state where we have the initial state Vi. So we can actually see that for the constant multiplying Vf is Pf Vf raised to the gamma, that's what we substitute there, and Pi Vi raised to the gamma is what we substitute for this constant multiplying Vi. But nevertheless the values are equal, are the same, because all of that is a constant. So now if we try to simplify, that's you see Vf and Vf are the same basis, so we just simply add up the indices, and that gives us gamma plus 1 minus gamma, which is 1, and that's why we have Vf there, and that's the same for Vi, because we have gamma plus 1 minus gamma, which is just Vi. So that's the work done. Now you can see that from here delta U is minus W. So now when we substitute W in that expression, we have delta U equals to minus what we have calculated for W. And now when we multiply this, when this minus sign affects the denominator here, and that gives us PFVF minus PIVI raised divided by gamma minus 1. So that's our delta U for that process. A horizontal cylinder equipped with a frictionless piston P is separated into two compartments A and B by a fixed wall P0. The setup made up of the cylinder, the piston and the wall is adiabatic. The piston is subjected externally to atmospheric pressure considered uniform and constant. Initially, the compartment A of volume VA contains n moles of an ideal gas at a pressure P0. The compartment B of volume VB is empty, negligible pressure. A very small orifice is created on the fixed wall P0 so that the piston can move very slowly. In a first instance, we suppose that VB is small enough to avoid the piston coming up against and knocking the fixed wall. Calculate the volume delta V swept through by the piston while the gas evolves to a final equilibrium state characterized by the volume Vf1 of the two compartments. Now our answer there should be A. Let's try to find out how to get that piston cylinder assembly. Now we can see that this first compartment has volume VA, the second compartment has volume VB. Now when the piston moves and sweeps a volume delta V, this is where the piston now lies. So we can clearly see that at the equilibrium state, from the piston to the end of the cylinder, that section should have a volume Vf1, and we can call this intermediate volume between this barrier, that's the wall that separates A and B, and the piston now at this state to be Vc. Now from the diagram, we can see that delta V plus Vc equals to Va. So you can see that this volume plus this volume is supposed to give you Va. So you see delta V plus Vc must be Va. So that gives us the first equation. And also, if you look keenly, Vf1 is given by this volume Vc plus Vb. So you see that if you add this volume and this volume, you should have Vf1. Now when we take equation 1 minus 2, you just simply see that the Vc cancels out, and we have delta V minus Vb to be equal to Va minus Vf1. Now making Vf1 the subject, delta V the subject rather, we have delta V equals to Va plus Vb minus Vf1. So that should be the volume swept by the piston when the gas moves to its new equilibrium state.